learning. As everyone in this audience knows, machine learning has proven itself across industries, from clinical diagnostics and financial forecasting to logistics and public safety, delivering accuracy as high as 95% in disease prediction, savings of 30% in inventory carrying costs, and so on. Wherever it can be deployed effectively, prediction accuracy is sharpened, planning is streamlined, and costs reduced. Yet, despite these well-known successes, conventional machine learning remains fundamentally hobbled because it lacks a scientific and mathematical foundation. Therefore, it's constrained to pattern recognition. It struggles with model bias. It requires complex and recurring model creation that are merely black boxes to the business, and often resists integration into real-world business workflows. Scientific machine learning can change that. It offers a rigorous foundation rooted in the logic of science. Scientific machine learning, SML, is exactly solvable mathematically and is therefore universally explainable. In SML, probabilities and probability distributions aren't estimated, they're calculated exactly. We'll explore how scientific machine learning moves us from empirical modeling to deductive human intelligence, and why that shift matters for the future of decision-making, risk management, and scalable business deployments. Let's go to the next page. So business at its core is about counting what counts. When we tally states, count events or units, the result is always a whole number, a multiple of the smallest comfortable unit of measure. 23 refrigerators in inventory means exactly 23 refrigerators, not 23 plus or minus some small amount. And so we can say that there are 23 refrigerators with supreme confidence. Let's take another example. Consider a pile of sand and an unlimited supply of identical empty cans. To measure the volume of the sand, we fill each can to the brim, skimming off the excess back into the pile to avoid loss. And we repeat this process until the remaining sand is less than a full can. That remainder is immeasurable, not because it's unknowable, but because it falls below our unit of measure. In the end, we count the number of filled cans and get an exact answer. So confidence in the human ability to count what counts is not new. It gave rise in the 19th century to the science of counting, which was a breakthrough that founded electronics, or what they called at the time the theory of electricity of circa 1850, and led to advanced science. I'm thinking of J. Willard Gibbs as a good example. So the science of counting is known, but scientific machine learning is an elevation of the science of counting, where the historical time series, so counting with timestamps, is integral with the science of counting. SML or scientific machine learning will always include the data. It will never exist without data. Now, operationally, with the science encapsulated in web services, so you don't have to look at it all the time time series is uploaded to the service, and a set of complete measurements are returned. In real time, it's not the loading of a web page. It takes a little more than that. This is machine learning, but it can take about 30 seconds or up to 5 minutes, depending how much data you have. Those are the limits. So this is essentially, you can think of this as a multimeter in the cloud. In summary, SML integrates user-supplied counting data with deductive logic to eliminate the exclusivity of ad hoc statistical model building, and at the same time provide complete mathematical transparency. So scientific machine learning, we're going to look at two particular measurements that seem to be very well suited to business forecasting. And those two exact measurements from the science of counting is the probability distribution function, so capturing the likelihood of outcomes with precision, and the demand distribution function, quantifying the demand as a discrete countable signal. And we'll want to apply this to two applications, two practical applications for scientific machine learning that leverages the PDF and the DDF, namely the forecasting of sales of a consumer packaged good. We have that sales data and we can explore it in some detail. And also another application is in executive reporting of KPIs. So we'll see if we have enough time to get to both of them. But we'll go first with the sales. So what you see here, we're presented here with 5 years of sales data. Okay? For two interdependent consumer product goods, or CPGs. Coffee brewers, the sales of coffee brewers on a weekly basis are on the left, and the coffee pods that feed the brewers are on the right. Each product is measured in its own discrete, appropriate counting units. For instance, in the brewers, it's 1,000 divided by 10, so the brewers 1 here means 100. And for pods, it's in units of 100,000, so 1 here is 100,000. The raw sales data is plotted as a black curve, as the black curves in both of these plots, capturing the actual transactional counts over time. Superimposed is a green dashed curve representing the running average, the statistical equilibrium line. So when the data is close to that, the dashed green line, this is where the data behaves statistically, meaning it's just as likely to go up as to go down. That's what we mean by equilibrium. So we can think of statistics as a zone of probabilistic balance, where, as is typical in statistics, all the states are viewed as equally likely, the indifference principle in statistics. The key realization here is that sales data rarely behaves statistically. It's often driven by promotions, seasonality, supply chain disruptions, or consumer trends. These deviations from equilibrium are not noise, they're signal. And the scientific machine learning is uniquely equipped to extract that signal without introducing ad hoc analyses. Because the data is countable, the deductive system evades any need for parameters or curve fitting or regression. Instead, it just doesn't have any room for it in the mathematics. Instead, we compute exact probability and demand distributions directly from the data. This allows us to forecast not just what might happen, but what is most likely to happen, grounded in counting. So in the particular, we're going to look at the analysis in a little more detail. What we're going to do on the next slide, we'll calculate the PDF for pods. So we're looking at the right-hand plot, and we're looking at the right-hand edge of that right-hand plot. So the latest data that I have, and what we want to, and the value of the dashed green curve on that right-hand edge is the origin of our next plot, where we plot the probability distribution function and the demand function as well. Right, so first thing, the red plot is the probability distribution function. You'll notice both the demand and distribution function, those are both, they're not continuous. Because we're counting, we have explicit points, it's discrete. And as I mentioned previously, the average now is the origin. So I'm making all my measurements from the average, and I'm counting the number of units for, in this case, for pods, that I move above that average. Now, these probability, each point here, each unit of measure above an average, I can calculate the probability exactly for that unit value. And as you would expect, when I add all those probabilities for the probability distribution function out to infinity, it of course adds up to 1. And this is because it's an infinite sum, it is guaranteed to do that. This is calculated as an infinite sum. So, so this is, now what's particularly nice, I think, about this is that because the probabilities are exact, the 99.9 percentile that people often use for instance, for risk management, that's exactly determined. I know exactly where that is. It's not, there isn't a plus or minus. It's an exact value. And also the expected value for the demand is also calculated exactly. So this is the interval that businesses use to manage their companies, the risk in their companies, is that value between the expected value and the 99.9% value. So this is a very clear canvas on which to do analysis, which is a step up. Now, for the demand distribution, what we're doing there is it's quite simply, it's the expected value, it's the unit step, right, which are multiples of my unit, multiplied by the exact probability, right? So it's one term in the expected value, and that each point, therefore, for each unit and each probability, I get an exact value for the demand. Okay, so that's how the demand function is created. Now, one thing I'll say here is that with probability distributions, you've seen one, you've seen them all. They all look very, very similar. The differences are very subtle, but those subtle differences have a big impact on the demand distribution. So those are the elements of the key elements of the plot. Let me make a few more comments about it. Oh, here we go. Sorry. So we've described the plots. Now that I have the probability distribution function, let's set the demand aside for a moment and just look at the probability distribution function, which is exact. This could now be used in a number of Monte Carlo, in environments with a Monte Carlo simulation. So for instance, the first thing to do would be just to take that probability distribution and import it into the customer's Monte Carlo environment, and from this probability distribution, create a set of paths. And those paths then would be used for your forecasting analysis. So that's the first thing you could do. Very easy. You have the exact. So what it do? It replaces the estimated probability distribution, the subjective probability distributions that are used today in Monte Carlo, with the exact mathematical result. So that's the first use. The second use would be where scientific machine learning takes that probability distribution and calculates the paths itself. So calculate 1,000 or 10,000 paths, but each of those paths is going to be consistent. It will be compatible with the science of counting. So this is a much smaller set of paths that can be created, and they're all consistent with scientific machine learning. All right, so those are the two quick uses, very obvious uses of how to introduce the probability distribution into Monte Carlo analyses. Now, I want to point out another thing. Notice that the peak of the demand, that it is not, if we were in fact in equilibrium, if this system were in statistical equilibrium, then that peak would be right on top of the average, right? And it's clearly not, right? And so there's clearly energy that's entering into the system. And that's really the key reason why statistical analysis doesn't work, is because when you look at a real time series in business or in life, whatever those time series may be, it's almost always there's energy entering or exiting the system. It's very rare that, in fact, you have to, as a scientist, you have to create that environment of statistical equilibrium. You rarely get it for free. So that's the, so this is the expected, so there's energy entering into the system, and we have to be aware of the fact that we could have energy entering and exiting. And one of the measurements of of scientific machine learning is, in fact, the energy. So you know exactly how much energy is going in or going out. Now, but it's the moment that energy is entering into the system. I'm now going to explain why I'm using demand here, is that in fact, the moment that energy is entering into a system, the expected value, which is what we're usually interested in, has a brother, has a partner. It's the expected strain. And you can't, only when you're at statistical equilibrium could you ignore the strain. But in every other case, you have strain. We can calculate it exactly. And not surprisingly, the strain is what leads to regression to mean. Right? Not a regression analysis, but the force. That brings me back to the mean. So that's both. We have to consider both the expected value and the expected strain, and they're of equal importance. But they also combine to create the natural coordinates for scientific machine learning. So a linear combination of the expected value and the expected strain defines demand, right? And I have a different combination of the two that defines the supply. So I now have expected demand and expected supply defined. For simplicity here, I've only plotted the expected demand, and I'm going to set the expected supply aside. Now notice here also, so that explains the origin of the demand. This is not new. You'll see this in very good books in like probability theory, the logic of science by E.T. Jaynes. This is also, you'll see demand and supply derived in a similar way. Now, of course, also here, every new data point that we add to our time series can be added to the previous time series and reprocessed by SML, so we can follow the dynamics as we move forward. All right, so that's the first. I won't say anything more about this plot, but I will move to. Let's go back quickly to the brewers and pods. These things are obviously related to each other, right? I mean, if you buy a brewer, you're going to need pods to operate it. So it's not surprising that when you get a big peak in brewers, you'll see a little later, you'll see a lot of pods also sold. So I think it's intuitively obvious that these two are closely related. And indeed, when we look at so the blue again, that's demand. I'm just repeating that. That's the demand for the pods, right, that we've looked at. And now the green is the demand for the brewers. And you'll see they're not quite the same. They're not actually using the same units, but the expected value you'll see is not the same. So the demand for pods is slightly bigger than the demand for brewers. So that's so now I can take individual time series and I can compare them, and I can see what is the expected value for each of them, and see which ones have greater demand or lesser demand. But okay, so that I can do. That's a comparison of time series, but I can also now take those time series and calculate the conditional probability for them. So the red is in fact is the number of pods given information about the brewers. about how many brewers are being sold. So if I increase the brewers, I would expect an increase also in the number of pods. So the red curve or discrete curve is that conditional probability or the conditional value for pods given brewers. In the upper right-hand corner, you'll see that that this really summarizes what we're doing. This is kind of an interaction diagram. This really summarizes what it is. It's a visual statement of Bayes' theorem is really what it is. And from this, we can calculate all of the conditional probabilities and at each time step. So let's move on from, so these are interactions is what we're doing. We're looking at the demand interactions, and they can be calculated exactly. Let's go to the next one. So this one is exactly what you would do for optimal control. This one's quite interesting because a lot of you realize that there's a lot of sailing analogies that start to appear in the science of counting. Because it starts right in the beginning when we define demand. We said there was expected value and there was expected strain. The strain is what's pushing back against the force that's pushing up the value. So it's just like keeping a sail in the same place and driving a boat forward. But beyond that, so what that does, when I do balance the demand with the expected value, or the change in expected value with the change in demand, you can plot a line. It turns out that you can derive it in a number of different ways, but you can calculate exactly the angle from the average, right? The green dotted line, dash line, and calculate exactly what that angle is. That angle is the optimization. It's how do I get the greatest increase in sales for the least effort, and by effort here I mean probably least money is really what it means. And so this is and you can see it performs very well. If you could stay on that expected on that blue dashed curve, which by the way is also it corresponds to thermal equilibrium as well. So if we could stay on that blue dashed line, we could actually use our statistics again. But in practice, sales, in operations doesn't usually work this way. This requires a lot of discipline from the sales and marketing organization, and they'll always want to try to get more out of the system. It's interesting to get the best result for the least effort, but what happens if I put a little more effort in? What can I do? So this actually can also be calculated where we take into account seasonality and the customer defines when they start high season, when they end high season, when they go into low season. All of this is defined by the customer, so it's not something that can be automatically put into a web service. But when you do that analysis, you'll see that if I could stay on the point here is that you always want to try to stay well above that green dashed curve. If you go below that, then the probability that I'll go up is less than 1/2. And the further below you get that the green dashed line, the worse it gets. So you really want to try to stay above the green dashed line all the time and never go below it. And if you can follow the blue dashed line, then you get that little increment, and from going above the blue line, and so which I call a stretch and a release is really what we're looking at here. So I drive the system and then I relax it back down to the blue dashed line, and then we go again. So this really changes the nature of optimization, is really how you chart your course. and how you spend your money. Now, I think it takes a very special person to make this work, somebody who really knows the operational environment for sales in this particular example, and knows how to move the levers, and also has the authority to drive an engagement like this. So we've had people who have companies. The coffee company has done some work along these lines, but there's a long way to go. But it can be applied in a lot of different areas. Wherever there's time series, you could do the same type of analysis. It's not specific to sales data. All right, so let's talk a bit more about in general what this comes. So we can use this to summarize what we've said up to this point. You can think of, if you've heard the term before, a one-armed bandit. It's a term, slightly disparaging term, that's used for slot machines in Las Vegas. Bandit, because it's pulling money out of your pocket. And what an n-armed bandit is, are n of those bandits, 10 of those bandits, each with one arm. Okay, and what we typically do, right? So when I pull, let's just look at one-armed bandit, one-armed bandit. When I pull the arm, there are a number of different things that could happen. I could get 777, it gives me one result. I get 3 bells, it gives me another return. So there are clearly, with one pull, there could be a number of different things that happen. And that's captured by the probability distribution. That will explain, what type of return you could expect. But the big assumption in n-armed bandits, because this is the reason why I'm talking about bandits, is because this is the fundamental model, or the fundamental it's the fundamental analysis, right, behind reinforcement learning, right? So this is the basis of reinforcement learning. But with reinforcement learning, it's always, you assume that the probability distribution is constant. It doesn't change with time, right? So every time I pull the arm, that probability distribution will be the same. And it also assumes that there's no interaction between those one-armed bandits. So if I pull on one arm, it's not going to affect its neighbor or some other one-armed bandit. So those are very severe limitations, constraints, and it works. We have a huge number of n-armed bandit problems that are solved. It's been very useful, but in practice, if you look at the real data, everything is really changing with time, and it often happens that things interact with each other. So this goes beyond this. What we've described with scientific machine learning goes beyond reinforcement learning. In fact, it returns back to Richard Bellman's work in the 1950s, who's often referenced in reinforcement learning. But we return to his work on his famous work on dynamic programming in the 1950s. And returning to that, the big difference, though, between the scientific machine learning and Bellman is Bellman's analysis was functional analysis. He used mathematics, functional analysis in mathematics, to figure out what type of functional forms things had to take. But he didn't calculate probabilities exactly. In fact, what he would do is he would assume that the percentage was the probability. But the percentage is only the probability when you're in statistical equilibrium. It's never equal to the probability when you're not in statistical equilibrium. So all of this now allows a whole new set of problems to be looked at. Okay, the first thing, so let me just mention the problems here. Just using the n-armed bandit, it's been applied to many, many problems. I have a list of them: online advertising, clinical trials, recommender systems, portfolio management, adaptive routing. And if you look at all of them, in fact, they're making an assumption that everything is static and that there are no interactions. So this is now a huge opportunity. Anyone who's written one of these systems before, it would make a lot of sense to generalize it to where probability distributions can change and where there are interactions. So that's one set of applications that would be pretty easy to upgrade. And then The other applications are the ones that go back to Bellman. So those are allocation problems. And there are an enormous number of allocation problems that have been looked at, even in Bellman's book. He mentions inventory and stock level, investment management, sequential testing, cargo loading, cattle breeding, and so on. And anyone who's read the book will know that there's an appendix at the end that lists all the different applications. So this is a very small sampling of what you can do in a dynamic version of dynamic programming. So SML promises to do exactly those problems with this exactly solvable, mathematically solvable special case of what Bellman did, counting what counts. Okay, so I've lost track of time. I'm just going to mention one other thing and then open it up for questions. Just state the obvious, another opportunity. This might not be quite the right crowd, but where there's probably the greatest benefit to a business environment, so our economic well-being, is if this were implemented in executive reporting. So executive reporting, of course, are the KPIs, the key performance indicators that senior leadership uses to develop quick, well-informed, strategic and tactical decisions. This could be an application that provides society with its greatest economic good, since after sufficient study, this doesn't happen overnight, but after sufficient study and parallel reporting, companies now can transition their business decisions away from the invalid statistical assumptions to the correct probability distribution. In this context, key performance indicators are discrete, countable signals of organizational health, like units sold, customers retained, incidents resolved, dollars earned, often expressed as percentage, right? Percentages, so conversion rates, retention rates, utilization rates, and so on. These rates are treated by the executives, senior executives, as probabilities, but they're not actually probabilities if the underlying data is not statistical. So, as I've claimed, and we've seen actually in some of the plots we've already looked at, that the business data rarely behaves statistically. So therefore, scientific machine learning offers a corrective. It replaces or runs in parallel statistical proxies that we use today with the deductive probabilities calculated directly from counting what counts with supreme confidence. Okay, so let me stop there.